Tonight, we are not going to look at something bright. Not a star, not a planet, not even a galaxy. Instead, we are going to focus on something you have never seen, and yet, it may be the reason galaxies exist at all. Right now, as you look at the night sky, it feels like the universe is made of light, stars, glowing gas, distant galaxies. But that impression is incomplete, because most of what holds those structures together cannot be seen. It does not shine, it does not reflect, it does not leave a visible trace. And yet, without it, the Milky Way would not hold its shape. Galaxies would not form the way they do. Clusters would not remain bound. The large-scale structure of the universe would look entirely different. Something invisible is shaping everything. Tonight, we are going to trace it, not by looking at light, but by following motion, gravity, and structure, until the outline of something hidden begins to emerge. There is no rush. Just listen and let the visible universe soften for a moment as we move into a part of reality that has always been there but has never been directly seen. The story did not begin with mystery. It began with a problem, a quiet one at first, hidden in measurements, buried in the motion of stars. When astronomers began tracking how stars move within galaxies, the expectations seemed simple. Gravity should behave the same way it does everywhere else. Objects closer to the center should move faster. Objects farther away should slow down. That is how motion works when most of the mass is concentrated in one place. And for a long time, no one had a reason to doubt it. But when the data became precise enough, something didn't match. The outer stars were not slowing down. They were moving just as fast as the stars closer to the center, sometimes even faster than the visible mass of the galaxy could allow. If those measurements were correct, those galaxies should not have remained stable. They should have begun to drift apart, slowly unraveling over time. But they didn't. They remained intact, rotating quietly, as if something unseen was holding them together. The story did not begin with mystery. It began with a problem, a quiet one at first, hidden in measurements, buried in the motion of stars. When astronomers began tracking how stars move within galaxies, the expectations seemed simple. Gravity should behave the same way it does everywhere else. Objects closer to the center should move faster. Objects farther away should slow down. That is how motion works when most of the mass is concentrated in one place. And for a long time, no one had a reason to doubt it. But when the data became precise enough, something didn't match. The outer stars were not slowing down. They were moving just as fast as the stars closer to the center, sometimes even faster than the visible mass of the galaxy could allow. If those measurements were correct, those galaxies should not have remained stable. They should have begun to drift apart, slowly unraveling over time. But they didn't. They remained intact, rotating quietly, as if something unseen was holding them together. One of the astronomers who helped make this impossible to ignore was Vera Rubin. By the 1970s, Rubin and her collaborators were studying the rotation of spiral galaxies with increasing precision. Not just one or two exceptional systems, but many. The pattern was remarkably consistent. Instead of dropping with distance from the center, the rotation curves stayed flat. The outer regions of galaxies behaved as if they were still deep inside a strong gravitational field. That meant mass was continuing outward, far beyond the bright disk of stars. Not in a narrow band, not in isolated clumps, but in a broad, extended distribution, a halo. This was a profound shift in how galaxies were imagined. Before, it was easy to think of a galaxy as mostly what you could see, a shining disk, a bulge of stars, clouds of gas, perhaps some faint outer structure. But the motion suggested something much larger. The visible galaxy was only the illuminated center of a more massive system. The stars marked the brightest part, not the whole thing. Around every major galaxy, there seemed to be an extended envelope of unseen mass, diffuse, enormous, dominant. Today, that idea is so familiar that it can sound almost ordinary, but it is not ordinary at all. It means that when you look at a galaxy, you are not seeing most of it. You are seeing the luminous component nested within a much larger invisible halo. The stars are not freely drifting in empty space. They are moving through a gravitational landscape largely shaped by something else. That hidden component is now thought to account for about 85% of all matter in the universe. Not 85% of everything, because the universe also contains dark energy, but of all matter, of the material that contributes mass and gravity in the ordinary sense. Only a small fraction is the familiar atomic matter that makes stars, planets, gas clouds, and living things. Everything human beings have ever touched, every stone, ocean, atmosphere, tree, mountain, animal, and world, belongs to the minority component. The dominant matter of the cosmos is something else. That alone is enough to change the emotional scale of the subject. We are not discussing a small correction to a known picture. We are discussing the possibility that most matter in the universe exists in a form completely unlike the matter we are made of. But if this matter cannot be seen, how do we know it is really there? The answer lies in what mass does. Mass shapes gravity, and gravity shapes motion. It also bends light. That means even something invisible can reveal itself indirectly if its gravitational influence is strong enough. This is one of the most important ideas in modern astronomy. You do not always have to see something directly to map its presence. You can infer it from how it affects everything around it. That inference is not vague, it is not mystical, it is measurable.
Stars move through gravitational fields. Gas clouds orbit within them. Galaxies cluster according to them. And light, even though it has no mass, follows the curvature of space-time created by mass. So if enough invisible matter exists in a region, its presence can be traced by motion and distortion. Astronomers began to assemble these traces from many angles. They studied the speeds of stars in galaxies. They measured how galaxies move inside clusters. They examined how hot gas behaves in large systems. They looked at how distant galaxies appear stretched or duplicated when light passes through massive foreground objects. Each method had different uncertainties. Each examined a different scale. And still, the same pattern emerged. There was more gravity than visible matter could account for. This is what made the dark matter idea so durable. It did not depend on a single experiment. It appeared across scales, within galaxies, within galaxy clusters, across the large-scale structure of the universe. even in the oldest light we can observe from the early cosmos. A single odd result can be ignored. A repeated discrepancy across many methods cannot. The evidence accumulated not as a sudden revelation, but as a convergence. One clue after another, one measurement after another, one system after another. Together, they outlined something never seen directly, a hidden architecture, not made of light, but of influence. If you imagine traveling outward from the center of a galaxy, the visible scene would gradually change. You would pass the dense central bulge where stars are crowded together, then the graceful spiral arms, then the outer disk where stars become fewer and the darkness between them grows wider. Eventually, the visible galaxy would seem close to ending, but gravitationally it would not be ending at all. You would still be inside the halo. This halo is not like a shell or a surface. It has no visible boundary, no sharp wall, no familiar texture. It is a vast region where invisible matter dominates. The halo extends far beyond the stars, far beyond the glowing gas, far beyond what most images of a galaxy suggest. And this matters because the halo governs motion. Stars in the outer regions move as though they are embedded in a larger mass distribution than the luminous galaxy reveals. Without that hidden mass, their speeds would be too high. Over long timescales, the outer structure would not remain stable in the same way. The galaxy would be different, smaller, less bound, less persistent. Dark matter halos also shape how galaxies form in the first place. They are not merely support structures added after the fact. They are part of the conditions that allowed galaxies to emerge. Ordinary matter can cool, collapse, fragment, and form stars. But before it does that efficiently, it must gather. Dark matter provides the gravitational wells into which visible matter falls. In that sense, stars form inside a pre-existing framework. A galaxy is not simply a luminous object floating by itself. It is the visible expression of matter settling into an invisible gravitational scaffold. This changes the meaning of what we see when we look out at the night sky. A galaxy is not just an island of light. It is a bright concentration within a much larger dark structure. The visible parts are real, but they are incomplete. And because every large galaxy appears to sit inside such a halo, dark matter is not a local oddity. It is woven through the universe at every major scale where structure exists. The evidence becomes even more dramatic when we leave individual galaxies behind and look at galaxy clusters. A galaxy cluster is one of the largest gravitationally bound structures in the universe. It can contain hundreds or even thousands of galaxies, enormous clouds of hot gas, and a vast reservoir of unseen mass. Clusters are powerful because they allow several kinds of matter to be studied together. The visible galaxies are visible in starlight. The hot gas glows in X-rays, and the total mass can be inferred from gravitational effects. When astronomers compare these components, the mismatch becomes impossible to overlook. The visible galaxies do not provide enough mass. The hot gas adds more, but still not enough. The total gravitational pull remains much stronger than all visible components together can explain. Then there are collisions. When galaxy clusters collide, they create one of the clearest natural experiments available in cosmology. The galaxies within each cluster are relatively sparse, so they can pass through one another without frequent direct collisions. But the hot gas behaves differently. Gas interacts electromagnetically. It collides, it compresses,
it slows down, it heats up. So during a cluster collision, the visible gas can be dragged and displaced. If all the mass were tied to that ordinary matter, the gravitational center should stay with the gas. But in some famous systems, that is not what happens. Gravitational lensing maps show that most of the mass continues forward with the galaxies, not with the slowed gas. This means the dominant mass component does not behave like ordinary matter. It does not collide strongly. It does not stick. It passes through with relatively little resistance. That observation is extraordinarily important because it tells us dark matter, if it is matter, is not just invisible, it is dynamically different. It does not participate in the electromagnetic interactions that govern ordinary gas, plasma, chemistry, and light. It responds primarily to gravity. That is a much more specific statement than simply saying we cannot see it. It narrows the possibilities. Whatever dark matter is, it is not just faint dust, not hidden stars, not ordinary gas we somehow overlooked. Those possibilities were considered long ago. They do not fit the evidence. The dominant mass of the universe must be something fundamentally unlike the luminous matter we know best. Another path to dark matter comes through light itself. At first, that sounds paradoxical. How can light reveal something that does not interact with light? The answer is gravity. According to general relativity, mass curves space-time. Light follows that curvature. So when light from a distant galaxy passes near a massive object on its way to us, its path bends. This is gravitational lensing. Sometimes the effect is subtle. A distant galaxy appears slightly stretched or sheared. Its shape is gently distorted. No single image looks dramatic, but across many galaxies, the pattern becomes statistically clear. This is called weak lensing. In other cases, the effect is much stronger. A single background galaxy may appear duplicated into arcs or rings around a foreground mass. Its image is bent into luminous curves. This is strong lensing. Both forms are useful. They allow astronomers to map mass directly from its gravitational effect without needing that mass to emit light. That is what makes lensing so powerful for dark matter studies. A region of space can look almost empty in ordinary images and still produce measurable distortions in the light behind it. From those distortions, astronomers can reconstruct where mass must be located. Again and again, the maps show more mass than visible matter alone can explain. Not just a little more, a great deal more. Lensing also reveals how dark matter is distributed on large scales. It appears in halos around galaxies, in extended structures around clusters, and in the great filaments that connect cosmic structures together. In this way, light becomes a kind of tracer for the invisible, not because dark matter shines, but because its gravity silently reshapes the paths that light takes through the universe. You never see dark matter itself in these observations. What you see is the visible universe warped around it. That is a subtle difference, but an important one. Dark matter remains hidden, yet its fingerprints are everywhere. If we continue outward, past galaxies and clusters, we arrive at one of the most striking images in modern cosmology, the cosmic web. On the largest scales, galaxies are not scattered randomly through the universe. They form a pattern. Long filaments stretch across immense distances. Clusters gather at intersections. Between them lie vast, emptier regions called voids. This pattern is not decorative, it is physical structure. and it encodes the history of how matter gathered over cosmic time. When scientists simulate the universe from early conditions shortly after the Big Bang, the outcome depends strongly on what kinds of matter are included. If only ordinary matter is used, structure forms too slowly. The resulting universe does not resemble what we observe well enough. But when dark matter is included, something remarkable happens. The simulations generate filaments, clusters, and voids that look much more like the real large-scale cosmos. Dark matter acts as the first major scaffold. Because it does not interact with radiation in the same way ordinary matter does, it can begin clumping earlier. Its gravity amplifies tiny initial density differences. Over time, those variations grow. Filaments emerge. Nodes become clusters. Voids expand where matter is sparse. Later, ordinary matter falls into these dark structures. Gas collects in the gravitational wells. It cools, fragments, forms stars, then galaxies. In this picture, visible structure grows inside invisible structure. The first stars do not create the framework, they illuminate it. That idea changes how deep space images can be understood. When we look at galaxies scattered across the sky, we are not simply seeing isolated objects. We are seeing bright nodes in a larger pattern. The luminous universe outlines the hidden one. Each galaxy marks a local concentration. Each cluster marks a deeper well. Each filament traces a route where matter has gathered over billions of years. And between them, the voids matter too. Voids are not just empty places, they help define the shape of the web. They show where matter did not collect strongly. They reveal the contrast that gives large-scale structure its form. So even where light is scarce, dark matter still shapes the geometry of the cosmos. It determines not only where galaxies are, but where they are not. To understand why dark matter became so important in cosmology, we have to go back even farther, to the early universe. In the beginning, the universe was hot, dense, and nearly uniform. Nearly, but not perfectly. Tiny fluctuations in density existed. Small regions were just slightly denser than others. Those tiny differences mattered enormously. Over time, gravity can amplify density differences. Denser regions pull in more matter, becoming denser still. But ordinary matter in the early universe was coupled strongly to radiation. Light and matter were interacting intensely. That interaction made it difficult for ordinary matter to begin collapsing efficiently right away. Dark matter, if it exists and does not couple to radiation in the same way, would behave differently. It could begin forming gravitational structures earlier. That early advantage changes everything. Dark matter would start building wells in the cosmic landscape before atoms had fully decoupled from radiation. Later, once the universe cooled enough, ordinary matter could fall into those pre-existing wells. This helps explain how galaxies formed early enough to match observations. Without such a hidden component, it becomes harder to grow structure quickly enough from the small fluctuations seen in the early universe. This is one reason the dark matter idea is not only about modern galaxies, it is tied to cosmic history from the beginning. Measurements of the cosmic microwave background, the faint afterglow of the early universe, also support a cosmos in which ordinary matter is not enough by itself. The patterns of temperature fluctuations in that ancient light contain information about the universe's composition. Those patterns point toward a universe where most matter is non-luminous. So, dark matter is not inferred only from late-time galaxies or local motion. It appears in the universe's oldest large-scale evidence as well. This breadth matters. Any alternative explanation must account not just for one anomaly, but for an entire network of observations: galactic rotation, cluster dynamics, gravitational lensing, large-scale structure, and the early universe background itself. That is why dark matter remains so compelling. It does not solve a single puzzle. It helps hold together many different pieces of the same cosmic picture. Naturally, once the evidence became strong enough, the next question followed immediately. What is it? And here, the story becomes stranger. Because dark matter is not just invisible in practice, it may be fundamentally difficult to interact with. One family of ideas proposed that dark matter is made of new particles, particles not included in the familiar set of protons, neutrons, electrons, and the ordinary atomic matter they compose. Among the most discussed candidates for many years were WIMPs, weakly interacting massive particles. The name captures the concept well. Massive, meaning they carry substantial mass compared with very light particles. Weakly interacting, meaning they rarely interact with ordinary matter except through gravity and perhaps the weak nuclear force. If the universe were filled with such particles, they could pass through ordinary matter almost unnoticed. Trillions might move through your body every second without leaving a sensation or obvious trace. That sounds extraordinary, but it fits the basic requirement. Dark matter must be massive enough to shape gravity. It must interact weakly enough to remain unseen in ordinary electromagnetic observations.
Another candidate is the axion. Axions are imagined as extremely light particles with properties very different from WIMPs. Rather than behaving like heavy, slow individual particles in the intuitive sense, they may act more like a subtle field spread through space. Under special conditions, axions might convert into photons in the presence of strong magnetic fields. This possibility has inspired highly specialized experiments. Then there are sterile neutrinos and other more exotic candidates, particles that extend beyond the standard model of particle physics in different ways. Each candidate has its own predicted mass range, interaction pattern, cosmological behavior, and experimental signatures. What they share is a common role. They offer a form of matter that could be gravitationally significant while remaining largely hidden from light. For a time, WIMPs were among the most favored possibilities, in part because they fit elegantly into some broader theoretical ideas in particle physics. But despite decades of searching, no confirmed direct detection has emerged. That does not mean dark matter is false. It means the space of possibilities is shifting. Perhaps the particles are lighter than expected, perhaps heavier. Perhaps they interact even more weakly than early models assumed. Perhaps they require detection methods unlike the ones first designed for them. The absence of direct detection does not erase the gravitational evidence. It sharpens the mystery of what kind of thing could produce it. This is why some of the most sensitive dark matter experiments are not in space, but underground. That choice is deliberate. If you are searching for an extremely rare interaction between an invisible particle and ordinary matter, then the surface of Earth is a noisy place.
cosmic rays strike the atmosphere. Radiation from space and from the environment creates a constant background of events. To reduce that noise, scientists build detectors deep beneath mountains or rock. The overlying Earth acts as a shield. In those quiet chambers, instruments wait for the faintest possible signal. A dark matter particle passing through the detector might, in principle, collide with an atomic nucleus or an electron. That collision could produce a tiny flash of light, a small electrical signal, or a minute vibration in the detector material. The challenge is that such events, if they happen at all, are exceedingly rare, and many ordinary processes can mimic them. So the experiments must be exquisitely careful. They use ultra-pure materials, cryogenic temperatures, layers of shielding, redundant sensors, statistical analysis designed to separate possible signal from background. The result is one of the quietest forms of listening in science, and so far, that listening has not yielded a universally accepted direct detection. Year after year, the instruments have become more sensitive, limits have improved, possible parameter ranges have narrowed, some candidate models have become less plausible, but the definitive event, the unmistakable interaction that would reveal dark matter in the laboratory, has not arrived. That silence is scientifically valuable. A null result is still information. It tells us what dark matter is probably not, or at least what it is less likely to be under certain assumptions. But emotionally, it deepens the tension, because the universe appears full of dark matter in its gravitational behavior, and yet the laboratory remains quiet. This creates one of the central asymmetries of the field. Astronomy says something is there. Particle experiments say it is not easy to catch. Both statements may be true at the same time. That has led some scientists to consider another possibility. What if the missing mass is not missing mass at all? What if the problem lies in our understanding of gravity? This family of ideas does not deny the observations. It tries to reinterpret them.
If gravity behaves differently on very large scales or very low accelerations, then perhaps galaxies rotate the way they do without needing large amounts of unseen matter. This is an attractive thought in one sense. It replaces invisible matter with modified laws, and laws, unlike hidden particles, can sometimes feel cleaner. But the universe is not obligated to be emotionally satisfying. The question is not which explanation feels simpler. It is which one explains the full range of evidence best. Modified gravity ideas can account for some galactic scale behaviors rather well in certain cases, but the challenge grows when the evidence broadens. Cluster collisions, gravitational lensing maps, early universe structure formation, and the cosmic microwave background all place heavy demands on any alternative model. It is difficult for a modified gravity theory to explain all of these as successfully and consistently as dark matter currently does. That is why, despite continued interest in alternatives, dark matter remains the leading framework. Not because it is complete, not because it is directly detected, but because competing explanations have struggled to replace it across all scales at once. This is important to understand. Dark matter is not accepted because scientists enjoy mysterious, invisible ingredients. It is accepted because the universe repeatedly behaves as though such an ingredient exists. If a better idea comes along, one that explains galaxies, clusters, lensing,
cosmic structure, and early universe observations more completely, science will follow the evidence there. But so far, the evidence keeps returning to the same broad conclusion: there is more matter than we can see. Even within the dark matter framework, important questions remain. One of them is whether dark matter interacts with itself. For a long time, the simplest models treated dark matter as essentially collisionless. It responds to gravity and mostly nothing else. That assumption works surprisingly well on large scales, but on smaller scales, especially within the central regions of some galaxies, the details are not always perfect. Simulations based on simple cold dark matter can predict dense central concentrations in halos. Yet some observations, especially of smaller galaxies, suggest shallower cores than expected. This does not necessarily mean the main framework is wrong. Ordinary matter complicates the picture. Stars form, supernovae explode, gas flows in and out, energy is injected into galactic environments. All of these processes can reshape the visible structure of a galaxy and may also alter the distribution of dark matter indirectly over time. So when a mismatch appears, there are at least two broad possibilities. Either dark matter itself has additional properties, or ordinary baryonic processes have modified the halo enough to create the observed difference. To sort that out, astronomers compare many galaxies across many environments: large galaxies, small galaxies, quiet galaxies, star-forming galaxies, galaxies in dense regions, galaxies in relative isolation. They look for patterns that remain stable across these differences. If the same discrepancy appears under many conditions, it may point to a property of dark matter itself. If it varies systematically with star formation history or gas dynamics, then ordinary matter may be doing more of the sculpting. This is a subtle frontier. It is no longer just about whether dark matter exists. It is about what kind of dark matter could produce the structures we observe most precisely. Perhaps it is almost perfectly collisionless. Perhaps it has weak self-interactions that matter only over vast timescales. Perhaps it forms small-scale structures differently from the simplest models. These are not dramatic departures from the central idea. They are refinements. But refinements matter, because eventually understanding may come not from one spectacular detection, but from many small constraints narrowing the possibilities until only a few remain. As the field has matured, one thing has become increasingly clear. Dark matter is best understood as a problem of constraints. We do not begin with a known object and study its details. We begin with effects and ask what kind of thing could cause them. That means every observation places a boundary around the answer. It must have mass. It must be largely non-luminous. It must not interact strongly with electromagnetic radiation. It must help structure form early. It must be distributed in halos and larger filaments. It must survive from the early universe until now. It must behave consistently across immense scales. These requirements are powerful. They do not tell us exactly what dark matter is, but they sharply limit what it can be. This is why the search has continued for so long without collapsing into chaos. Dark matter is mysterious, but it is not unconstrained. The universe has already told us a great deal about its behavior. We know it is not ordinary matter in disguise. We know it is not just an observational error. We know it cannot be a tiny local effect. We know it shapes cosmic structure broadly and persistently. What we lack is not evidence of influence. What we lack is identity. And identity is harder. In most of science, identity comes from direct interaction. You shine light on something, you scatter particles off it, you measure its spectrum, you isolate it, you observe how it responds. Dark matter resists that sequence. Its most obvious behavior is gravitational, and gravity is a broad collective effect. It tells us where mass is. It tells us how much there must be, but it does not easily reveal microscopic composition. That is why dark matter can feel like a shadow cast by the structure of space-time itself, not because it is unreal, but because we encounter it through consequences rather than contact. There is something philosophically unusual about that. Human beings are used to trusting the visible. Even in science, many foundational discoveries eventually become things we can isolate, measure, manipulate, or image in some direct way. Dark matter has not yet crossed that threshold. It has become one of the most important components of modern cosmology, without ever appearing in a detector in a universally agreed direct form. That makes it feel unfinished. And in a sense, it is unfinished. We can map where it must be. We can estimate how much of it exists. We can model how it shaped structure across cosmic history. But when we ask what it is made of, the answer falls silent. This silence can be misleading if we are not careful. It is easy to imagine that because we do not know what dark matter is, we know almost nothing about it. In fact, the opposite is true. We know a great deal about how it behaves on large scales. We know it is stable over billions of years. We know it clusters gravitationally. We know it dominates matter halos. We know it does not radiate or absorb light in any ordinary way. We know it allows the universe to grow the structures we observe. The missing piece is not behavior at cosmic scales. It is microscopic nature. That distinction matters because it changes how the mystery should be felt.
Dark matter is not a vague supernatural unknown. It is a highly constrained physical unknown, a specific absence in an otherwise increasingly precise model. That is what makes it so compelling. The better our maps become, the stranger it is that the central substance shaping those maps remains unidentified. Future progress may come from several directions at once. One path is direct detection. If a new detector finally records an interaction that cannot be explained away, and if that signal is confirmed independently, then dark matter could move from gravitational inference into the realm of particle identity. Another path is astronomy itself. Large surveys now map millions of galaxies and measure weak lensing over enormous areas of sky. These observations reveal how mass is distributed statistically across cosmic time. As that precision improves, certain dark matter models may fit better than others. Another route comes from simulations. As computing improves, scientists can model structure formation with increasing realism, including both dark matter and the complicated feedback processes of ordinary matter. That may help clarify whether small-scale discrepancies come from the dark sector itself or from astrophysical processes inside galaxies. There is also the possibility of indirect detection. If dark matter particles annihilate or decay under rare conditions, they might produce high-energy photons or other particles that could be observed. Such signals are difficult to interpret because the universe contains many energetic astrophysical sources, but the search continues.
And then there is theory. Sometimes the limiting factor is not the data, but the framework used to interpret it. New particle models, new dark sector ideas, or new connections between cosmology and fundamental physics may reshape the field again. Perhaps dark matter is not a single particle species. Perhaps it is a whole hidden sector with its own internal structure. Perhaps it interacts weakly with itself in ways only subtle observations can reveal. Or perhaps the eventual answer will be stranger than current categories suggest. Science has encountered such moments before. A persistent anomaly remains, evidence grows, old assumptions narrow, then suddenly a new framework makes the pieces fit in a more intelligible way. Whether dark matter will yield in that manner is not yet known, but the search is not stagnant. It is steadily compressing the space of possibilities. And sometimes that is how understanding arrives, not in a flash, but through the gradual elimination of everything that cannot be true. There is also a more intimate way to think about all of this. Dark matter is not somewhere else. It is not only in distant clusters or remote galaxies seen through giant telescopes. If the current picture is correct, dark matter is present here too. Our own Milky Way sits inside a dark matter halo. The solar system moves through that halo as it orbits the galaxy. The Earth moves through it. You move through it. Not because dark matter collects in your room like dust, not because it gathers visibly around objects, but because the galaxy itself is embedded in a larger invisible structure, and everything within the galaxy travels through that environment. That idea can be hard to feel because there is no sensation attached to it, no sound, no glow, no resistance, no obvious local sign, and yet the larger motion of our galaxy depends on it. The stars in the Milky Way are not orbiting within a gravitational field generated only by visible matter. Their motion reflects the halo surrounding them. So even the familiar band of starlight that stretches across the night sky, the Milky Way seen from within, is part of a visible structure nested inside a hidden one.
This makes dark matter a different kind of cosmic presence. It is not hidden by distance, it is hidden by indifference. It does not respond to the sensory channels and instruments that first taught us how to know the universe. It is present, but not participatory in the ordinary luminous sense. That may be why the subject feels so quietly unsettling. It suggests that most matter does not belong to the category of matter we know best, that the material universe is not dominated by the kind of substance that forms atoms, chemistry, weather, oceans, rocks, bodies, and stars. Those things are rich and complex, but they are not typical. They are the bright minority. The dominant matter of the universe may be simple, dark, and nearly non-interacting, a background presence that shapes the stage on which visible complexity appears. If that is true, then the visible universe is not the full physical story. It is the luminous layer, the part that radiates, collides, heats, cools, condenses, and evolves dramatically. Dark matter does not do those things in the same way. It does not ignite into stars. It does not form glowing nebulae. It does not build planets or atmospheres or trees. Its role is quieter. It provides the gravitational framework. It shapes where visible matter can gather. It stabilizes structures. It influences motion across scales too large to ignore. All complexity unfolds inside that framework. That one-sided relationship is striking. Visible matter reacts intensely. It radiates energy. It changes state. It forms chemistry and biology. It builds all the intricate forms we recognize. Dark matter, by contrast, seems almost austere. It remains in the background, massive, persistent, structurally important, yet behaviorally simple compared with the bright matter we know. And because it remains in the background, it is easy to underestimate its significance. But without it, the universe would likely not have developed the same way at all. Galaxies might have formed later, or differently, or not in the structures we now observe. Clusters might not have held together in the same way. The cosmic web might never have developed into its familiar pattern. So, although dark matter is not the source of visible beauty directly, it may be one of the deepest reasons that visible beauty exists. The stars do not shine because of dark matter, but many of the places where stars shine may owe their existence to it. In that sense, dark matter is not just another subject in astronomy. It is part of the hidden precondition for the luminous universe itself. There may also be limits to what observation alone can do. This does not mean dark matter is unknowable. It means the route to knowing it may be unusually indirect. Every method we use depends on interaction. We detect light. We register charged particles. We measure energy deposition. We observe forces acting in ways our instruments can record. If dark matter avoids most of those channels, then progress may always come first through structure, statistics, and gravitational effects. We may come to know dark matter the way one learns the shape of the wind by watching fields bend under it, not by seeing the thing itself clearly at first, but by tracing what it consistently does. That is still knowledge. It is just a different kind. And perhaps that is why the subject remains so compelling at a human level. Dark matter sits at the border between certainty and incompleteness. The evidence for its influence is powerful. The explanation of its nature is unfinished. We are far beyond vague speculation, yet not all the way to direct identification. This middle condition gives the subject its tension. It is not an empty mystery. It is a disciplined mystery.
The universe has revealed the outline. The interior remains dark. That may not always be true. One future experiment may shift the field. One repeated signal may open a new era. One elegant theoretical advance may make the hidden component finally intelligible. But for now, we live in a moment where the cosmos seems to tell us something both precise and humbling. Most of the matter in existence does not present itself to us in the forms we once expected matter to take. If you step back from the measurements, from the equations, from the detectors deep underground, and the lensing maps stretched across the sky, what remains is something surprisingly simple. The universe is coherent. Its structure is not arbitrary. Galaxies hold together. Clusters remain bound. Light follows curved paths that can be predicted. Matter gathers into filaments and leaves behind voids. The cosmos behaves as though an invisible mass is present everywhere structure matters. Not occasionally, not in one special region, not in a handful of unusual systems. Everywhere. That is the quiet power of the dark matter idea. It does not rely on a dramatic single image. It does not depend on one lucky observation. It emerges from consistency. The same conclusion appearing from rotation curves, from lensing, from cluster collisions, from large-scale structure, from the early universe. Consistency is one of science's deepest forms of persuasion, and here, the consistency is difficult to escape. When you look up at the night sky, The stars seem to define reality. They are the obvious things, the visible things, the things that appear to fill space with meaning. But they are not the whole structure. They are the luminous fraction. Beyond the visible edge of every galaxy, between galaxies, through the filaments that span cosmic distances, there seems to be a larger presence, unlit, nearly silent, and essential. No telescope has given us a direct portrait of it. No instrument has yet delivered its identity with certainty. But motion points to it, gravity points to it, structure points to it. And perhaps that is enough for now to let the mind rest in a strange but steady thought that the universe we see is only the surface of a deeper arrangement, a bright layer resting within something darker and far more extensive, something that has been there since the earliest times, something that guided the growth of galaxies before stars fully lit them, something that still surrounds those galaxies now, shaping their motion without ever revealing a face. So when you imagine drifting through the Milky Way, past its stars, past its dust, past the final visible traces of the disk, you do not enter emptiness, you enter the halo, a vast region of invisible mass, a hidden extension of the galaxy, a reminder that the universe does not end where light fades. And when you look deeper still, to clusters, filaments, and the broad architecture of the cosmos, the same truth appears again. The visible universe is not the complete universe. It is the part that shines. The rest remains with us, not as color, not as texture, not as an image resolved by a lens, but as structure, as gravity, as persistence, as the reason galaxies do not fly apart, the reason clusters remain bound, the reason the cosmic web took shape at all. Something hidden, something ancient, something that does not need to glow in order to matter. And perhaps that is the most remarkable part. The universe is not held together only by what can be seen. It is held together in large part by something that never enters the light. So tonight, as the stars continue their quiet motion across the dark, you might remember that the darkness between them is not necessarily empty, that beyond every shining structure lies a larger, unseen one, that the night sky is not simply a display of objects, but a hint, an outline of an invisible design, and that far beyond the last bright stars and all around them, and even here, moving with our own galaxy through the dark, there is still something present, not visible, not resolved, not understood in full, but there, holding the universe in shape.